All right, we're going to go ahead and get started at this point.
Hi, this is Dave Leahy. Thanks everybody for joining us today. This is the DASI Solutions Problem Solving Seminar for Plastics. I'm Dave Leahy. I'm the Simulation Product Manager, kind of hosting this here today. Along with me is Shaun Bentley, our Application Engineer for the simulation tools, including SOLIDWORKS Plastics. And we're pleased to have Chris McDonald, who's a plastic engineer from the industry, joining us, and he's going to show us some models that he's been working on with some customers. Chris comes from Bluebill Engineering Services. They work with SOLIDWORKS Plastics to do a variety of simulations for customers. He's got 23 years of injection molding experience. He also works for Stone Plastics, and he's an instructor at Grand Rapids Community College. As you can see, he's got the requisite education and certification, including the RJG Master Molder. So we appreciate Chris for joining us today. So I think first thing to start off, we'll talk a little bit about why do simulation, why are we doing simulation at all. We'll be going into some examples, but really what's somewhat of the justification. And to start that, I want to start off with a poll question to kind of understand one of the things with the industry and what we sell into SOLIDWORKS Plastics is we dealt with a variety of people in different types of jobs, from part design all the way through product launch and quality. So we just want to do a quick poll to determine which one of these areas you happen to be part of. So if you basically just let us know what part of the industry you work in, please select that, and we'll get some results here in a minute. All right, looks like everybody that's going to vote has voted. So basically what we see here is that it looks like the majority of the people online are parts designers for plastic parts. We have a few people that work in the molding industry, and one customer actually does part design through injection molding. So great, thanks. So if we look at this, basically it involves a wide range, and the traditional way to use simulation had been in the past after you have built designed the part, had the mold built, designed and built, go ahead and put it into production, you start finding defects. I think you've all been here in this particular case, either as a part designer or as a molder, where you're going ready to make it and you're having some problems. In that particular case, you would often do a simulation, you'd outsource it, or in some cases you'd have the capabilities in-house. So they're fixed after the fact, but they may get fixed. In some cases they may not be, but it's costly and inefficient. I think we all understand that. What we've migrated to over time was people are validating existing designs. So the part designer, and a lot of you who are part designers, it looks like the majority of you, basically give it to the molder and they'll run a simulation after you've designed it. Then they'll make sure that they get any problems. They may come back to you and ask for some changes, or they say they can't make it, and they can know that by doing a simulation. That helps somewhat, but again, now the mold designer and the simulation are still decoupled. So there's a benefit to a small number of parts, but there's still basically an overall lack of optimization. So what we're going to talk about today is if we do it up front and the part designer does it, and it's also done all the way through the process by also the mold designer and the production house, you're able to optimize the part design, and this will help you get better parts, get them done quicker, reduce your product development time. And as we all know, again, this is one of the reasons why we're talking about simulation. The more we can, the impact of the change we can make a big change early in the process and it doesn't cost us much money, or a small change at the end of the process which may cost us a lot of money. So we really want to make those changes and iterations up front as part of the process. So with that, before we turn it over to Shaun, I've got one more polling question for you. And basically, we're just trying to determine those who've attending the seminar, have you used a mold flow or plastics molding type software in the past? So if you please answer this, and we'll share the results here in a minute. Looks like we're getting a variety of responses. All right. I'm going to close the poll here in a second. And we'll share it with you. So basically, as you can see, we've got some people that have never used it. So it's pretty wide range of people. Looks like everybody in every step of this, every step along the way. So it gives us a good background to kind of reinforce how it can be used. So Shaun, I'll turn it over to you to talk about our first project that we're working on here.
Okay, great. Thanks, Dave. All right, so the first hands-on, or the first model I'd like to look at with you is a stool. You can take a look at the initial design on the right here, on the right of this slide. And it's a bit crude to start with, but what I'd like to do is we're going to figure out, is this thing going to fill? How much pressure is needed if it does fill? How much cooling time does it need on it? It's rather thick right now. And then we'll take a look at it if there's any structural defects. And we're going to go through this process iteratively. I'm going to start off with sort of a basic, crude idea of what I want to create for a stool, and then I'll make improvements. So for the first iteration, I'm starting off with the design, then I'll move into a plastics fill simulation, and then I'll move into a brief structural simulation. I want to focus more on the plastics segment for this presentation. But and then we'll just repeat this process once or twice and try to make improvements to the design in each stage. So in our case, I'm going to call this initial iteration 0. Here's our initial design, the crude first version, and then we'll do a fill. It's the fill. You can kind of see where I'm going to put the injection location for this fill right in the top center. Okay, it's going to fill it out. I'll walk through that in a moment, and then we'll do the structural simulation, and you'll see in the top, I'll see a lot of stresses up there as well. So we'll have to maybe make some design changes to reduce the stresses. So starting off the plastics simulation at this point. So here's this stool design. Again, rather thick. If I zoom in on one of its legs here and grab an edge, you can see the measurement depicted down here of close to a 1/4 inch thick. Okay, so it's pretty thick plastic. And if I use the SOLIDWORKS Plastics add-in, I've already turned on the add-in. I'll go to my plastics manager, and then here we can walk through this process basically from top to bottom. I'll start off by creating a mesh. If I go through some of the manual mesh controls, this will allow me to break the model up into simple pieces so it can analyze the full complex shape of it. And one of the key steps in here is to key in a mesh size. I'm going to make the mesh rather coarse so it runs fairly quickly, but I'll also do some automatic refinement. So if I create a mesh based on that, you can see how it automatically makes the mesh tighter in regions where there's curvature, especially wherever there's complexities, so it can get a better result in those regions. So that'll be pretty much all I do for the mesh for this example. And then next I'll move into defining my material. The polymer in this case is going to be polypropylene. So you can see here how many different material categories we have, and the one I'm looking for, of course, is the polypropylene. But if I sort of expand out a few of these, each one of these categories has 20, 30, 50 materials. So there's thousands of materials, and it's really the material that defines a lot of the setup for the study. If I go into the polymer properties here, you see, for example, that just by selecting this material, it's recommending a mold temperature of 50 Celsius, a melt temperature of 230. So remember those two numbers for a moment, because I'll pull those up in the fill settings. But you see, a lot of the setup is already defined just by selecting the material. So now if I go to the fill settings, you can see it's already keyed in the mold temperature of 50 and the melt temperature 230. I can, of course, customize it at this point, but I'll just use the material defaults for now. Next, I'll define the injection location, and this is going to be right at the top center. I've created a couple split lines, so it just makes it easier for me to grab right in the middle, but basically you can grab wherever you want. It'll select a node wherever I'm clicking, but I'll put it right in the center, and I'll add that. All right, so at a basic level, that's pretty much all you need to do as far as the setup is concerned, at the very basic. Now, there's a couple different ways we could run this study. If I want to do flow and packing, simulate the packing phase, or if I want to do flow, packing, and also simulate warp after the part leaves the mold. In this example, I'm just going to run the flow analysis. And in here, this analysis takes maybe a little less than a minute here, but you'll see that it'll give me previews every 10% or so that it runs. It updates this preview graphic. Now, if I run the packing phase, in addition to the fill phase, it's going to simulate the additional 20, 30, 50 seconds of packing pressure that I might apply to this type of a model. So it'll actually cool down during that phase, and we'll be able to get a more accurate sense of how much sinkage we'll get if we were to use the packing result. And then the one additional phase we could run is cooling. With cooling, you're allowed to model in cooling lines. This current study just assumes that the mold is kind of a constant temperature of like 50 degrees Celsius. But with the actual cooling module with plastics, you can simulate the cooling lines and actually include and mesh the mold, and then it'll actually give me the temperature profile and the heat transfer coefficients all to that mold as well. So a bunch of different phases. Once again, the summary: fill, pack, warp, and cooling. So this analysis is nearly complete. As it's wrapping up here, again, you can sort of preview the results at its current stage, but it looks like it's just getting done now. So if I go ahead and just close out of that solver window, we can see what some of the results look like. If I take a look at the fill animation, it sort of looks like that slide I had earlier. Okay. Now, other relevant parameters to what I was looking for, I want to see how much packing pressure was required. In this case, about 19 megapascals. To put it in perspective, the yield strength of steels usually varies between about 100 to 1,000 megapascals, somewhere in that range. So, so 19 megapascals the pressure required here. Then if I go to cooling time, you can see how long this thing takes to cool. It's almost 100 seconds. You know, with as thick as it is, it's maybe no surprise that it takes so long. And additionally, you can kind of tell where there's going to be weld lines, if there's any structural defects on this. As I fill it, you can see where these flow fronts come together here. So there should be a weld line there. If I turn on this weld lines checkbox, we can see here and here, these are where there might be a little bit of a structural weakness because of how the melt fronts come together, but they don't mix around to where it gets a homogeneous connection point there. So you do get a little bit of a structural defect potentially. And then one last parameter maybe I'll show while I'm here is air traps. You can see in the bottom of the model. And if I made a symmetric mesh, I think that the air traps might be a little more symmetric in this case. But you can see mostly in the bottoms of the model where the flow front finishes is where we might have air traps, potential air traps. Okay. So those are some of the key results I wanted to show you to start with. A lot of other things I could play around with in there, but so next one I'd like to show briefly is just the structural simulation that I've already pre-run. I won't go through all the setup of that, but just want to make the primary focus on the plastic side of things here. So on the structural side, if I run a structural study, you can see the loads that I have. There's a 200-pound force on the top here, and then down here I've got 100 or 50, 100 pounds down here to simulate somebody resting their legs or even putting a lot of their body weight onto one of these little armatures. So if I look at the factor of safety distribution, or maybe first start with the stresses, actually. If I look at the stress distribution, you can see high stresses. So right up here, down here seems to be okay. Not quite as high a stresses as you see up here. And if I go to a factor of safety plot, we see that the factor of safety in this case is right around 3.5 or so. You can kind of see the coloration. 3 is red, and we're somewhere in this red-orange area up here. Okay, so getting close to a factor of safety of 3. So it looks like it might hold, but I had to make it really thick for it to be able to hold that, that weight. So next what I like to do, I guess before I jump to the next portion, one of the main points I want to make about the having SOLIDWORks and SOLIDWORKS Plastics and also even a structural analysis tool all together in one environment is it really saves a lot of time of having, you don't have to translate models back and forth, having them all in the same spot. You can just set up each study and hit run and then make a change to your design and do this iteratively, which I'm about to show next. So let me go ahead and move to our next iteration of this design, try to improve it. So I made 3 design changes. One change I made to this stool is I added ribs to the understructure, stiffen it up, add some strength to that bottom. Okay, so something I think probably pretty obvious to many of you watching, but really helps with increasing the strength. Then another thing I did, I increased the strength there, but I also reduced the thickness, so that kind of compromises the strength a bit, but it should really help with the cooling time. Okay, so originally the thickness was about 0.24, now the thickness is going to be about 0.14. Okay, we'll see how much does the cooling time get cut in half or something, or what's the relationship there. And then also I adjusted the leg design a little bit to improve the stability. I made the leg a little bit thicker here. You see it's 1.1 originally. I made it 1.6 or something to make it a little bit larger. And I moved this this little piece here up a little bit so it makes the leg a little more stable, so it's not able to twist and buckle quite as easily with this thing shifted upward. So I'm not going to run all these analysis. I'll just show you the results I got when I ran them. So going through these same 3 phases, here's the kind of results I ended up with. So to do the comparison here, see the original factor safety of 3.5 is what I had on the first design, and actually I've improved the factor safety, even though I made it thinner. By adding the ribs, stiffening in it, adding more strength up here, it actually improved the factor safety up to about 4.5. Plastic cooling time went down to about 1/3, okay, 1/3 the cooling time roughly. The mass even went down, okay, but the injection pressure did go up a bit because it is thinner after all, so it does require a little bit more push to get the plastic to fill it. So you see that a little bit more than doubled in this case. Now something I want to point out in this slide is that you see this is showing the factor safety here, so this is sort of the high stressed regions. You see very low stress here, the very good factor safety here, but over here we can see that we're starting to get some stress on this little armature. And if you remember, that's where we had some of these weld lines. I know this might have a sort of an Escher look to it maybe, but you see I've rotated, I'm looking on the underside. And you can see the leg here with the little bit high stress region, and you can see that same leg here, okay, where the weld line's located, right in the center, right through the middle. Okay, so I don't want there to be high stress, of course, where there's a weld line. So what I'd like to try to do is shift the weld line around a little bit. One technique I might try to get it to move around is to change the injection location. So in this case, the injection location used to be right on center. If I'll try moving it over to a point like here, and that does shift the weld line a little bit. Okay, so you can kind of see how it's coming together down in this region if I make that injection here. Okay, so here's where that new weld line. So it shifts it away from the center a bit, and then I think that the main point of simulation is to be able to test out all these different ideas to see what helps, what doesn't help, that kind of thing. Okay, rather than having to cut steel to figure all this stuff out. All right, so once again, really want to hit this point here that that it's an all-in-one environment. You'll be able to do your design in SOLIDWORKS, run a plastics fill analysis, and also run a structural simulations all together So it should save you a lot of time, also reduce a lot of mistakes, because when you have to translate things, you may have to set up the whole study over again. You might, it becomes tedious, and potentially it might make mistakes and forget to add a load here that you usually add, that kind of thing. So it really reduces the chance of making mistakes, and saves a lot of time back and forth. So next, what I'd like to do is turn it over to Chris McDonald, and he's going to show a little bit of a couple of projects that he'd worked on. So let me change the presenter over to him.
All right, thanks, Shaun. Hello, everybody. I just want to show you a couple of examples of projects that I've been working on with some of my customers that kind of go along with what Dave and Shaun have already been saying of using simulation up front. The first example that I have is a project where the tool was already created and they had an issue with the part, namely sink, and then we're wanting to use simulation to be able to see if they could make improvements to it and if they even could to begin with. This was a scenario where the injection molder was being called out by their customer saying, hey, you need to get rid of these sink marks. The molder was saying, well, it's based on part design. So pretty much what happened is running simulation to see if there could be an improvement and if there could not be improvement. So what we have here is a small part. It's basically a zipper pull where you grab a hold of the back section and it's attached to either a zipper or something like that. A little bit of an enhancement of what Shaun showed is that I actually modeled in the screw, the runner, and you see a small cashew gate going up into the bottom side of the part. The one example for this is that the customer really wanted a small gate to eliminate vestige, because obviously with the design of this part, grabbing a hold of it, they didn't want the end customer to be able to feel any kind of gate vestige or any kind of a bump or anything on the underside of that part, so the gate location had to be relatively small. So in this scenario, the simulation was more about, okay, if we ran a normal packing pressure, and I'm just going to go to pack settings here and go to pressure profile. We're currently running at about 7,000 plastic pressure of pack for about 2 seconds. This is a very normal, very consistent way of packing the part and normal setting on the molding machine. So we're going to go ahead and I'll just show you the flow results. Go to an isometric mode here, and I'm just going to play it. So what you see is you can see the cavity is filling in the third dimension. You see going up through the cashew gate and then going ahead and filling the part, going out to the end. One more time. So I'm going to pause it right here so you can see with SOLIDWORKS Plastics you can get a very, very detailed view of what the filling pattern looks like going through the part. So when we get to the end, I'm just going to flip over to the warp side and the sink mark profile. This is the piece that the customer really wanted to understand and to know. Running the given normal set pack pressure on the molding process, you can see the sink mark profile is about 0.0016 inches deep. Doesn't seem like much in reality, but when you look at when you talk about a plastic part, you can certainly see that sink mark on the surface of the part itself, which is what the end item customer was concerned about. So through simulation, I was able to replicate what the injection molder was actually running. Then, of course, asking the question, well, could we really be able to eliminate the sink even if we packed it at its maximum machine capacity? So again, what I have is the same part. Pretty much in this instance, I'll open up the flow again. Again, you can see the same general flow pattern. That's of course in the 2-dimension. Going back over to the warping and the sink mark profile. So for this particular example, if we look at the pack settings on this one, we maximize the packing pressure on the molding machine to 19,000 psi, which is for this particular machine was the actual maximum pressure, and then also increasing the time. So the scenario was if I maximize the pack pressure and increase the time, do I get improvements in sync? So having those settings, going back to the sync mark profile, as I rotate this part, what you see is you still see sync marks on the end of the part, even though we packed it at the maximum setting of the machine. So we had a very small improvement in the sync mark profile from 0.0016 before to 0.0015 now. So the reality was that the injection molder was able to go back to their customer and say, well, even if we pack this part at this maximum machine capacity, you're still not going to be able to get rid of the sync marks. So at the end of the day, this is a very good example of why you want to do simulation, specifically using SOLIDWORKS Plastics to be able to do this scenario up front before you cut steel. So at this point in time, the ability to improve the sync mark profile is going to have to go back in and do part design changes, which now becomes very expensive and very difficult now that the steel has already been created. One other thing that I wanted to show you was the gate location. Basically, when you do 3D modeling of a part in a runner system, you basically create that gate location at the end of the screw. Just like Shaun had showed you before with the split faces, same thing that you put on the end of the screw to create that the gate location. Again, with SOLIDWORKS Plastics, you can change fill speed, pressures, temperatures, and to simulate and do those iterations to be able to really understand what process parameters really affect the quality of the part. And at this point, I'll turn it back over to Shaun.
All right, thank you.
So thanks, Chris. That was great. Yes, that did illustrate kind of the first example I showed when we talked at the beginning, where it's done at the end, where everything's designed, tools cut, and we run a simulation to try to determine, hey, can we fix this? In some cases you can. In this particular case, they weren't able to. But they were able to get some good feedback and probably gave them some ideas for how they would do things in the future. The next thing we want to talk about is optimize the molding process for a chair back. A little bit similar to the one Shaun showed with a stool, but this was a real world example that Chris worked on with another customer. So we'll turn it back to Chris.
Okay, so this particular example is a chair back, relatively thick part. Again, the design where the customer wanted to create this design of the chair. Also, the biggest concern with plastic chairs is having a weld line here right up at the top. The design of the chair was created so that when somebody grabs a hold of the chair, moves the chair, stacks the chair, they're grabbing a hold of this integrated handle up at the top. And the one thing that the customer was very concerned about was having a weld line at that particular location because of, one, it could break, two, having either some flashy in the fill where it could be a sharp edge or something of that nature. So for this particular example, the customer wanted to be able to evaluate valve gates. So, and specifically sequential valve gating. So SOLIDWORKS Plastics certainly has the ability to do sequential valve gating, and this is a very particular example of where we can get that done. So if I rotate the part around, you'll see two gate locations. So you see one gate location here at the bottom, kind of in the seat of the chair, and also we have a gate location up here at the top. One of the concerns the customer had too is that they didn't want to see nit lines going through basically this section of the part. You can imagine if you sat on this chair and leaned back into it and you had a weld line going straight across the chair. Of course, that's a weak point, and that weak point could certainly end up breaking, and the last thing you want to do is have somebody falling over backwards off of the chair because that nit line was weak. So customer wanted to really evaluate, one, is sequential valve gating the appropriate tool? And two, can we concentrate the weld lines up here at the top corner? If so, what's that going to look like? So with SOLIDWORKS Plastics, I'm not going to go through all of the individual settings, but the one thing that I do want to show you is how you actually very easily simulate valve gates. So I'm going to injection location. You can see up here in the corner we have 2 injection locations. So main injection location number 1 is down on the bottom of the chair seat. Location number 2 is up here at the top of the chair. Just as a side note, originally the customer thought that they were going to need 3 valve gates. Again, one right here in the center of the part, but through simulation, I was able to show them that 2 gates are more than plenty. Of course, saving on tooling costs and valve gate technology, cylinders, everything else. So that was certainly helpful for them. So the second gate location, we have a setting down here of the injection range. So with SOLIDWORKS Plastics, you have the ability to change when this valve gate here starts to fill the part. This happened to be worked out at 80%. The reality is through multiple iterations, 60, 70, 80, 90, you can certainly change this setting to be able to see where you ideally can place the nit lines for this particular part. I'm just going to go ahead and I'll run the flow simulation. So here's the flow results. I'm going to turn on isometric, and we'll just go ahead and play it. So what you'll see first is initially starting to fill at the bottom of the seat. When the part gets to about 80% full, you'll see this valve gate open up here and continue to fill. So I'll just run the flow simulation. So you can see right at this point, it's about 80% full. This valve gate opens up. Once that valve gate opens up, it starts to fill at the top. Once you've done that, now you have no nit line right here at the top of where you would grab a hold of the chair. Ideally, what the customer was looking for. Again, continue to play. You see there is some weld lines. So it's about SOLIDWORKS Plastics. Now I can just back off, and now I can manually adjust where we see the fill times. So starting to fill at the top, you're going to see weld lines through here on the corner of the chair. I'm going to run it forward just a little bit more. So you can start to see the weld lines start to knit together here. No weld line here where the customer is actually very concerned. So we're going to get a weld line here, and then 2 in the center where you would expect going around the hole. So as those 2 weld lines come together, we can turn on the weld line feature. And again, you see exactly where those weld lines are coming together. So of course, you can see the weld line on the back and then certainly the weld line on the front. So very good tool to be able to evaluate where your weld lines are going to end up. Again, customer did not want to see weld line going straight through the center of the part, which there's not. Certainly didn't want to see a weld line going through the center of the handle area of the part either. So again, with simulation, being able to really take a look at it and evaluate where those weld lines were going to occur, just to make sure that those weld lines weren't in location.
All right, so let's move on to the runner balancing next, I think.
Okay.
Great. Let's see, show my... All right, so next thing I'd like to take a look at with you is a runner balancing example. This is another example that Chris had run through. We couldn't get permission to show the exact customer file, but I've basically made a simplified version of the idea of this runner balancing to demonstrate what Chris had run into for his particular customer. So the example I'm going to show you is just 3 very similar parts, and then one that's a little bit different, has a couple extra features on it that'll, if I were to use the same size runners leading up at all the parts, then you would guess that, of course, this one's going to take the longest to fill. It's got the most volume to fill. So my goal in the runner balancing scenario is to try to equalize when all these 3 items fill. So let me show the rough idea in SOLIDWORKS. So here's that same model. You see I've drawn a 3D sketch to depict the runners, and then I'll use plastics to convert those into runners. I'm not going to walk through all those details, but for now, just due to time. But basically, you go through this channel design section, and then it'll allow you to select the lines, and maybe I'll open it up for just a moment. So you can kind of see the runner system, and you can set up the initial point and final point diameters for each one of these line segments. Okay, so I've already done that ahead of time, and initially I made them all equal to each other, and when I ran it, I got a result that looks kind of like this. So as it's filling up, you can kind of tell this one fills faster than that one. So if you watch carefully, you see this one closes and then that one closes shortly after. But if it is hard to see because they're pretty close in time. But if I go ahead and just tell this to go from 7 to the end, you can really see the difference here. Okay, so you can see the fill time depicted on this color chart. Right around the yellow region is what I'm seeing here is kind of yellow. So it looks like that gets done filling at around 7.5 ballpark, whereas this one takes a little bit longer to fill up. It's at around 7.7. Okay, so just this small difference in time can create large differences in pressure requirements to fill it. For example, in this scenario, we have about 50 megapascals required, and you can see the asymmetry in the pressures. And you see this one's this pressure here looks quite a bit higher. You know, for some reason, it's completely opposite of this guy. Okay, so very interesting. So now what I'll do is I'll run the runner balancing, and with the runner balancing tool, I tell it how many iterations. It's going to automatically change these diameters and try to figure out where is it balanced. At what point does it balance the fill time between all three of these or all four of these parts? Okay, so it's going to run a bunch of iterations for me automatically to figure out what it should key in for those diameters, and I can specify these other parameters to tell it just to stay within my machinable bounds. Okay. So it'll basically run the study a bunch of times, so it does take a little while to run. So I've already run this runner balancing scenario, and when I run it, it'll give me a message. Okay, once it completes, it'll say the runner balancing analysis is completed. Before, there was a difference of about 0.2 seconds, which we saw. I mean, it was 7.5 to 7.7. So before, there was a difference of 0.2 seconds between the fills. Now there's only a difference of 0.01 after I tried to 0.02 after I tried to balance it. And then here was the difference in pressure before, and now it reduces it down to 0. So let's see what that looked like. So if I go to that scenario here, so looking at the fill time, so maybe you can kind of tell. Looks like they both fill simultaneously, but to be a little more sure, let me bump it up to this range so you can see the roughly red regions in both scenarios. Now it's not yellow-red kind of. They're both red, indicating they're both close to this final fill time. And also, the pressures before were about 50 megapascals. Now the pressure required to fill this is much lower, only 32. So a huge marginal drop in pressure there, as far as percentage-wise. I mean, almost cut the pressure in half, just with that little bit of balancing. It'll also display the thicknesses that it decided on. Okay, before I was using 6, but now you can see a little tricky to see from these graphics, but it says 6.08, and on the other side it's 5.96, 5.97 roughly, 5.98 on the other side. So little differences in the other ones, but it made this one, definitely made this one a little bit bigger to balance it out. So
to kind of chime in a little bit, you know, as Shaun was running the simulation, this was very close to the same issue that I had with one of my my customers currently, where they had 3 parts that were identical, and then one that, you know, was slightly larger in volume, not much. Like I said, very similar to what you're seeing here. The reality of it is that as injection molders, with fill weight and fill balance, close isn't good enough. You have to be very accurate, because if you're not accurate, you can have flash on one part and short shots on another part. So fill balance is extremely important. And as you go through the field balancing exercise, I will tell you this, is that with the simulation that I created, first shots on this for my customer's mold was about 2.5 weeks ago, when they did a short shot analysis and compared that to the simulation. It was within 1% of the simulation. So I will tell you that SOLIDWORKS Plastics does a very, very accurate job in runner balancing, in the fact that I can see it in simulation, I can turn around, I can get physical parts from my customer and literally look at both of them side by side. Again, 1%.
All right. Thank you very much, Chris. All right. So next, we'll turn
It's
it
time
over
for questions and wrap up. First to summarize before we go to questions, part of what we tried to show you here today is if we use a SOLIDWORKS simulation up front as part of your design process, and then all along the way modeling your process, you'll be able to avoid late manufacturing defects, which can cost you a bit of money. It makes your overall part quality great and reduce your time to market. I think what we'd like to do, obviously, is if I'll be following this up with some emails, making sure. I appreciate everybody for attending. If you have some challenges that you're trying to resolve that you think SOLIDWORKS Plastic may help, reach out to us, and we'll be checking in with you, and let's see if we can help you with those things. Certainly may not help all of the problems that you've got, but we'd love to talk to you about them and see what we can do to help you with that. In addition, there's our contact information and Chris's contact information. If you have some simulations that you need run or you want to check on a few things, Chris is also available for that. And we can talk in detail later also about potential for acquiring the SOLIDWORKS simulation plastic software. So at this point, we want to open it up for questions. You look at the bottom right-hand part of your screen. There's a section here for questions. If anybody's got any questions, they can type them in.
There's a question about, does plastics have rotational molding simulation? No, it's we're just simulating just injection molding, not many of the other types of molding that you have out there. Not rotational molding at this time.
So hang on for a few more questions.
Yeah, we'll hold for just a moment, see if there's any other that pop up. Maybe 30 seconds for if there's any other ones.
We thank everyone for attending today. If we don't have any other questions, we'll turn your day back over to you, and we can handle some things individually as we move forward. Thank you.
All right, sounds good. Thank you, guys.
Thank you, everybody.